Devin, you're just taking extra precautions.
I'm not muted. I'm in chapter 1 right now, so I'm being extra.
Oh, that makes sense. Good.
Yeah.
Hope the coffee.
Just home alone with my mask on.
Yeah. I hope the coffee's good. I haven't tried it out yet.
That's the best coffee.
Oh, good. Good to know.
Yeah. Stop by.
Morning, everyone. It's Friday. After I teach, you can play. Okay. See, we have like one gaming teaching station. So week 2, good? Everybody's still hanging in? Good. Me too. All right. Okay, Rowan, thank you. I'm gonna share screen just so I can get us started. Did you guys used to brush teeth in like other spaces besides the bathroom too? My kids like can't be away from the TV, it seems like.
All the time, honestly.
Yeah.
Mostly in the car.
Yeah, I'll eat on the couch, but I don't know about brushing teeth. Okay, can you guys see my Moodle site? All right, so I wanted to just orient us for our next week. And so today's the 12th, and we are, I promise, we're going to get into limits to organismal distribution. So the lecture today, I'll finish up our biomes. We'll go through kind of the marine systems. I'll do, a quick review, which I think might be, helpful for the quiz as well. And then we'll bust through the last of those aquatic biomes, and then we'll jump into limits to organismal distribution. And we have another day of that, scheduled for next week. So there's nothing really due in terms of homework associated with the limits to organismal distribution. It is going to feed into the biome lecture in that, you guys know why, plants and animals have, their own physiological tolerances. So they're not going to be found in every single biome. So we're going to speak a little bit about, temperature limitations, air, atmospheric, circulation, ocean circulation that can distribute organisms that live in the water, and rainfall limitations as well for certain organisms. So it all will feed into kind of that biome thing, at least the first part of it. So the non-living things that can influence where an organism lives. Later in that limits to organismal distribution lecture, we'll talk about how biotic things or living things, other organisms themselves, competitors, predators, think about invasive species. If an invasive species comes in, it'll limit the distribution of the native species. Are you saying hi? All right, you can say hi to everybody. They can't see you. Oops, I never know which way to angle. Okay, shut the door. Don't bother me. Okay. So, and then finally, after we think about how, living with other organisms is going to impact you, having the predators, the competitors, around, limit where you can be, then we're going to think about like the organisms themselves, like, can they move places? How do they disperse? It's easy to think of how a deer can move from one state to another, but, plants are kind of stuck. So that the only time they're really moving is via the wind, if they have those unique adaptations on their seeds, or if an animal kind of picks them up and carries them with them, or if we get them stuck on our clothes. I'm sure you guys have gone on a hike and had, all those like prickers that stick with you, those little burrs that stick, right, like Velcro on your pants. So that's kind of how we'll end that lecture. So again, we'll begin, feeding into the biome lecture with this limits to organismal distribution for the beginning of the week. And then we're going to roll into plants and animals, okay? The first test will include material probably on up through the animals. So there is actually no other homework besides the Biome 1 and whatever you guys are doing for lab, okay? Remember, lab next week is just a continuation of our human demography, right? So check in with your lab instructor if you're having any trouble, you know, finding your data set, organizing it and whatnot, but there should be a lot of good material on your Moodle site. Okay, so again, we won't have a test or anything, any homework or anything until the 24th. So you've got some time, okay? And like I said, I'm gonna try and get us through plants and at least into the animals for the content on that test. And right after we jump off of lecture today, you guys will have an opportunity to hop on if you want, just to get it over with, onto the quiz that's gonna be at the bottom of the Moodle site, okay? And should be pretty straightforward for you. Again, you'll have about 30 minutes while you're in the quiz, but you have until tomorrow at noon. So just plan ahead, you know, don't jump on at, you know, 11:45 tomorrow because you won't have enough time, okay? Again, if you're looking for additional information and you're looking for those lectures, you know, hop on this lecture overview page for the biomes and know that there's also one here for the limits to organismal distribution, okay? And so the lecture's right up top, and then some of the bigger take homes and some interesting little, you know, visuals and stuff will be on there, a little video and so on and so forth. So, you know, it always is a good practice to kind of go back and see what additional stuff I put up here for reinforcement. And there's a cute bunny. Okay. All right. The kids are screaming. So I'm going to start. Okay. Let's hop on our biomes and let's just quick, you know, pick up with the aquatics. So any issues, concerns, you feeling good about deserts, the forests, the savanna, grasslands? You're getting a sense of what the temperature and moisture is, what the soils are like, you know, what some of the overall adaptations are for those organisms. Keep those things in mind as you're taking that quiz. All right, in the aquatics, we mentioned we'd be covering freshwater, marine, which is, you know, ocean type stuff with salt, and some of the other interesting things, hydrothermal vents and mangroves, okay? We mentioned freshwater systems. The study of freshwater systems is limnology, and there's really like two types of freshwater systems, the lentic and the lotic, and remember, O in lotic for moving, okay? So our lotic, the moving water, we think river stream, but we knew that there were some interesting facets of a river and a stream, right? There's going to be some pools that are kind of pond-like, where the water is still, and you can imagine like debris can build up on the floor. And then there's going to be the fast moving areas where maybe it's very narrow and you're going to have a lot of rocks, and you can imagine there's more oxygenation in those kinds of, you know, riffles, they call them, in the moving water, the lotic systems. In the lentic, we're talking about kind of standing water, broad, you know, lakes and ponds, thinking about where, you know, Lake Champlain, our scenario. And we mentioned ice melt and so on resulted in a lot of these water bodies all over the place, but also beavers and us, you know, we create these water bodies. But another thing to note, again, the being near a big water body can kind of moderate the temperature in the city where you're located too, okay? Zonation, it's kind of important to memorize some of this zonation. Coastal, shallow waters where like plants can grow and stuff, that's the littoral zone in these lake type habitats. The limnetic zone is more like out in the middle of the lake, you know, or out, if you were in the ocean, kind of out there where hardly anything, you know, is going to be located except maybe the plankton, okay? The photic zone, you know, where the sunlight's going to hit, it's going to be up at the top, so everything's going to kind of, all the action's going to be happening up at the top. And the benthic is down at the bottom, benthic B, right? In terms of what we find living in the lake, you guys have probably, I'm sure you've looked under a microscope at our lake water, right? And hopefully you've never like gulped it and gotten a stomach ache. And but we have, you know, cyanobacteria, we have zooplankton. If you have an opportunity, if you're into this stuff, like the Lake Champlain Research Institute, my colleague Tim Myhook runs it. He hires students all the time to go out in the summertime, if you're local, out on the boat and help in collecting the zooplankton. But he also has students, all season and summer long and, each semester looking under the scope at water samples that they collect. So you can actually see some of these cool little organisms. Some are going to be totally photosynthetic, kind of plant-like, right? And then the others, the zooplankton, like zoo, right? These are animal-like. They're going to be consuming the plants. So zooplankton, phytoplankton. These are just some visuals of what they look like. There's a Daphne, a little water flea, very cute. And again, key zonation in these ponds, these lakes. It's going to be a function of the temperature of the water, right? And as how that compares to the air temperature. So there's 2 times during the year where the zonation that we normally see will change. It'll break up, okay? And so there's 3 zones to a typical kind of lake or pond system. The epi, like epidermis, the top part, warmer, that's where a lot of the action, the photosynthetic organisms are going to be because the sun's going to hit the top. Epilimnion. The middle, metalimnion. And then the bottom is the hypo at the bottom, limnion, okay? There's going to be some surface mixing and stuff, but there's also going to be a gradient of temperature, warmer at the top, cold at the bottom. You've probably felt it as you're walking in the water, right? And it's just going to kind of grade down. And as I said, that thermocline, that's what they call it, the thermocline, that change in temperature will go away twice, 2 seasons during the year. And as a result, those zones are going to flip. And that's really, really essential for any organism that's trying to photosynthesize at the top. It's at some point, it's going to have limited nutrients, right? They're going to grow so much, and then they're going to run out of nutrients. And so they need to get those nutrients, and the nutrients are from the dead organisms that have sunk down to the bottom. So when the lake thermocline breaks down, because the temperatures kind of become uniform, you'll see the nutrients flip. The bottom water and sediments, some of them will return to the top surface, and it'll give a pulse of nutrients to those organisms at the top, and kind of just shift everything around. And that's kind of essential in these areas to have these healthy habitats. And so you'll see that lake mixing, resuspension of all those nutrients, and that happens in the spring and the fall. Okay, this visual here showing the zonation in the winter, the zonation in the summer, but in the spring and the autumn, when there's these fluctuations in temperature, is when you start to see that thermocline break down, that temperature gradient break down, and the mixing occur, right? The hypolimnion moving up to the epilimnion and just shifting nutrients. So we also talked about, the photic zone, the organisms that live up at the top in that epilimnion, what's their situation? What do they look like? So a lot of them are going to be some macro vegetation. So think of your lily pads and stuff floating. You'll see the floating emerging vegetation, but a lot of it's going to be kind of microscopic, or you might see little like jelly blobs that are green. Chlorella is one of them. And these are, going to be able to photosynthesize, and they help us get a sense of the water quality in our lakes, okay? So they use a tool. You imagine you're out in a kayak or canoe, and you drop this disc, which kind of is a circle made out of, like plexiglass, and the plexiglass, imagine, half of it is white, and then there's triangles on it that are black. You drop it down, and you're looking, and on your string, there's going to be markings, right? So you'll kind of pinch where you all of a sudden can no longer see in the water column. You can't see this device anymore. You'll pinch your string, and then you'll roll it back up, and then you'll be able to kind of count how many meters it was, that you could no longer see. And that's going to give you a sense of how deep, how intense the amount of algae you have in your water body is. And again, like I said, it speaks to the nutrients, it speaks to the water quality of that water body. There's really 2 major states to keep in track of, okay? The 2 major states are the oligotrophic and the eutrophic, okay? eutrophic, you've probably heard of eutrophic lakes, right? When you have a really bad algae bloom, if say you go to Point Roche Park in the middle of the summer and all of a sudden you see the sign that says don't swim, don't let your dogs go out here and gulp up the water because they can get this toxicity. That's a eutrophic scenario. There's been nutrient pulse, temperature warms, conditions are good, the algae grow kind of in explosive numbers, and can hold these toxins. They kind of produce these toxins that can make us all sick. So in certain lakes, imagine, and we've been kind of thinking about buying a camp for the kids. Now that we have a camper, we're thinking like, let's plop it on land. So we're looking at a lot of lakes, and I'm like the worst person to be like a family member of, because my family decides, oh, look at this. This is great. Look at this beautiful lake. And I immediately Google New York State DEC water quality reports, right? To find out how many years there have been these harmful algae blooms, because you know what happens, you know, if you look at an aerial image and all these old camps are around, maybe some of them have these lawns, like lawns that lead down. Well, people will often, you know, be fertilizing the lawns, and then the fertilizer rolls off into the water body, or they have old septic systems, right? And they kind of dump it into the water body, and then you get this pulse of nutrients and these terrible algae blooms. And gosh, I want to kayak with the kids, right? I don't want our dog to die on our trip. So yeah, anyways, we haven't bought land. It's moral of the story. So that's eutrophic, right? So if it smells kind of sulfury, if everything looks green like pea soup, don't swim. And that would be a eutrophic scenario. So a lot of phosphorus, a lot of nitrogen has kind of run into the water. And as a result, you get these algae blooms, it's warmer temperature, and low oxygen causes fish kills. So you'll often see like fish kind of on the shorelines, which is not, you know, enticing. And then imagine over time, many years of all this algae, they die, right? And they drop down to the bottom, to the benthic kind of zone. And you start having the pond fill in, right? So you're like filling in with this sediment down at the bottom, which is kind of decomposed, you know, algae and whatnot. So anyways, that's a eutrophic scenario. The oligotrophic, think like you go up and you're hiking in the higher peaks and you come across a water body. It's pristine. You can imagine if you dropped your Secchi disc in, it would go forever, right? But it's probably got lesser nutrients in it, right? So you don't have these algae blooms, and that can limit what organisms live there too. But in general, it's probably a you know, healthier system. So phosphorus can be limiting, you know, low phytoplankton, low decomp rates, and so on. There's two other states. One is the dystrophic and one is the marl, okay? So dystrophic is the muckiness, right? Remember we talked about kind of the eutrophic one filling in. If you came to a pond that was like really just kind of a mud puddle almost, you know, it's just totally, you step in it and you get, it's like quicksand, that would be kind of a dystrophic scenario. And then a marl, I don't know, you know how I come up with these crazy ways to remember things. Like hard water, if you guys live in this area, you have to use like water softeners sometimes because we have a lot of calcium. And marl, when I think of marl, I think of like, you know, things kind of skeleton type stuff. And so imagine like the calcium, when it builds up, it turns to like a white crust, right? On your, when you look at your shower head, it's sometimes crusted in white, and that's a little bit of calcium buildup. So when calcium is high in these systems, in these water bodies, and starts to precipitate out, that's when they would call it a marl, okay? So really the key ones are oligotrophic and eutrophic, and then these other ones, you know, just be aware of what the terms mean, okay? But as you know, right, the more algae we've got, the more green it'll be. We won't see too deep with the Secchi disc, right? And that would suggest we have a eutrophic scenario. The alternative, as we can see deeper and we have less algae, is an oligotrophic system, Okay. Now, for organisms that are in these kind of still waters, these ponds, they have these adaptations we mentioned at different times of the day and night. They're going to be moving throughout the water column. In part, they'll move up to feed during certain times of the day, and then when they're done feeding, they'll go down back to the bottom so they can hide from predators. That's called diel vertical migration. So they kind of have this migration every day. They have this migration pattern. And then other times, like when it gets too hot or it gets too much nutrients, a lot of these zooplankton can go into these cyst forms. So, you know, like they just basically are like these dried, desiccated eggs that can burrow into the sediment. And then as soon as conditions restore, they can emerge. So imagine maybe it's waiting for turnover to happen, and then they can emerge into the state that they should be in to kind of move forward. Now the lotic systems, these are the moving, right? Oh, in it, moving water systems, and sometimes it's fast, but sometimes it's slow. It really depends like where on the river you are, okay? So we mentioned two different kind of micro habitats, tiny habitats within these river systems. Riffles being kind of the fast moving, is pictured right here. And then pools, imagine over here we had like a big log, right, that was blocking the flow, and it may be a turn, a bend. It's going to create this little like mini pond area of still water. So the conditions, oxygen, temperature, nutrient levels will be very different in a river system just between a riffle and a pool kind of microhabitat, okay? As we mentioned, the skinnier your river is, the faster the flow will be, just a pressure thing, right? And our worries for this kind of habitat would be degradation, things like the pollutants that we saw with the lakes and ponds, nitrogen and phosphorus, extra runoff, right? But also, you know, drugs being kind of flushed down the toilet and then entering into the wastewater treatment plant, which often can't remove some of those chemicals, and then they end up in, you know, being spilled out after they've been treated into these rivers, right? And then out into our lakes. Okay, so just a visual of your pool and your riffle type habitat, right? And again, the bottom of the river might look a little different, right? Your pools might have, you know, a lot of silt and muckiness, more like a pond would be. A riffle would maybe have kind of rough rocks, right? There's a little bit of erosion potential of the major substrate during that period of time. And what would the plankton scenario look like? What would the food chain look like? You're gonna have bacteria, you know, cyanobacteria, you're gonna have your protists, you're gonna have your zooplankton, and then you're gonna have fish that are gonna be in there eating all of these guys, okay? All right, so those streams start somewhere, and oftentimes, like in our area, they're starting up in the mountains where the snow will melt. And so first order, the term first order means like up where it begins, the headwaters, okay? So imagine up in the High Peaks area is the headwaters for the Au Sable River or the, you know, Saranac River. And so you can kind of see that, you know, if the headwaters is a 1, and there's branching throughout your rivers, right? The farther down you go, it becomes a 2 and then a 3 and then a 4 out into the lake, okay? And these orders, notice this is a 7th order stream. This is a first order, you know, stream segment. So narrow, fast flow, right? And this is wider, less flow, right? So there's different conditions. Imagine the organisms that live in a first order versus a later order stream, right? Let's think about light, speed of the water, the sediments, right? Temperatures, right? Low order, so headwaters up at the top of your mountain. You're in the forest, right? So it's shaded by the forest. It's gonna be cooler, and they're going to be narrow. I'm sure you've gone on a hike in the mountains and you guys have seen how like narrow those streams can be, right? And because they're narrow, the speed of the water might be faster. The sediments will be the rocky rubble, right? And you know, the surface area and volume of some of the organisms that you might find there might be higher, but the temperature will be cooler. Again, it's shaded and it's higher elevation probably. The higher the order, so the wider, like as we're heading out to the ocean or we're heading out to the lake, 7th order, 5th order, it's going to be less covered, right? Because it's wider and the water is going to be moving slower and so on. So again, think about the conditions that these animals and plants are living in and what they have to adapt to, okay? So let's look at a stream running from kind of 1st order, widening out as we get closer to where it's going to dump out, right? The ocean or the river or the lake. And let's just kind of look at the fish for now. We don't have to look at these, insects, these macroinvertebrates, but let's look at the fish, okay? When the river is narrow, check out what the fish look like. When the river widens, what are the fish looking like? What is the change you're seeing to their morphology?
They're bigger.
Yeah, it could be, a size difference. Also like a compression thing, right? I may have mentioned this quickly last time we met, but when the velocity of the river is fast, you want to be able to like just, let it go, over your body real quickly and not have a lot of friction, right? So you elongate, your body will be elongated and it'll just come right over you. And when you're like, everything's kind of still, your body doesn't need to deflect the speed of the water. And so what you end up seeing are more compressed bodies. So if anybody's seen like goldfish or koi, they tend to kind of be a little bit more, well, koi are a little bit longer, but like pumpkin seed sunfish, they're a little more kind of rounded in shape. They don't have to deal with that. And when you look at those macroinvertebrates, as I mentioned, if it's fast moving water and they're, the water and the organisms in the water are like jumping over rocks, then oftentimes you have organisms that will set themselves up like under a rock. I'm totally going to kind of give you a visual, and they'll spin a web. And so imagine anybody local, you go to Macomb State Park and you've seen there's a dam there, okay? We used to do a lab where we would go and collect, we'd take nets, we'd kick the sediment into the nets above the dam and below the dam. And we would see a totally different kind of group of organisms. And the ones below the dam, knowing the things are coming up and over, right? There are all these like web spinning kind of caddis flies that will pop in and out of these cocoons they'll cast their net and they'll catch the stuff kind of coming over. So, these little macroinvertebrates, they eat just like lions and tigers and deer, and right? They all specialize in different kinds of things and different little habitats, depending on where they're going to be located. So no need to memorize that. Just kind of remember me doing these crazy things. So again, their adaptations when these organisms are living in these habitats, they can filter feed the plankton out of the water. They can be active predators, kind of, when it's fast moving water, they can, gain benefit and momentum and attack. In more still water, they can kind of hide behind a crevice or a rock and then pounce onto their prey. So there's a lot of, unique little adaptations to the different kind of habitat they find them in, okay? Now the food web in these habitats, because the rivers tend to be more shallow than the lakes, right? There's actually going to be 2 places where they can get their food. So the organisms that are, swimming around in the river can get their food from algae and plants that are kind of floating, but then they can also get it from the muck that's down at the bottom, right? The nutrients that are down at the bottom, because it's not so separated. Imagine going out into the middle of Lake Champlain, it's very separated where the nutrients are located. So you'll have fish, you'll have your macroinvertebrates, you're going to have your, microorganisms like we talked about, the phytoplankton and stuff. But they've got a source at the top, and then they also are receiving, leaves that come in and then die and decompose, and there's nutrients that way too. Okay, so just a little more background on those cool, little macroinvertebrates. Nothing you need to memorize, but if you're into this stuff and if you're thinking maybe this would be a cool job, you can reach out to me. I can put you in touch with Tim Myhook. He's the director of the Lake Champlain Research Institute, LCRI, okay? But scrapers, shredders, collectors, there's the little web spinners right there, and so on, okay? Now, a wetland is a habitat that is kind of at the interface where land, terrestrial, meets the aquatic, okay? This is a wetland, okay? And you've probably been to several and maybe just didn't realize the term. There's 3 criteria to memorize with a wetland, okay? It must be wet. It must have standing water, okay? Otherwise, it's not a wetland. That's an easy one. It also needs to have soil that's different from the surrounding soil, okay? And then thirdly, it has to have plants that are adapted to being in the water, okay? So keep those 3 things in mind. I might actually at some point have you define them, okay? Got to have water, got to have plants that can tolerate the water, and then need soil that's different from the surrounding soils, okay? Now, there's many types. You can see there's lots of different types I've shown here, but there's many different types, and I kind of list them all here. And I think you'll remember and recall some of your experiences in them. So a marsh, I live near Ausable Marsh and Wickham Marsh, okay? It is a habitat that has a lot of emergent herbaceous plants, cattails, right? But you can also go to the beach, Cape Cod, Jersey Shore, and you can see kind of seagrass, right? You've probably been to New Jersey, or you've seen that there's grasses that are out in the water that helps, preventing storm surge, and it's actually really important habitat. But any kind of emerging herbaceous, grassy type stuff would be considered and categorized as a marsh. Now, if you live around here and you're like, wait a minute, I go to Ausable Marsh all the time, but there's trees. It looks like a forest to me. Yes, there's parts of it that are like bottomland floodplain, right? So anytime the dominant scenario is that you have a lot of trees in water, then we call it a swamp, okay? And over time, you'll see marshes shift to swamp, and vice versa if things change, all right? Riparian bottomland is, imagine like you're down in a certain part. I think this happens in Mississippi a lot. There are these flooded forests, right? That all of a sudden it's, you can walk for miles, but then certain seasons, you have to wear waders and the water is up to your waist and there's like snakes floating and all this crazy stuff. That's a riparian bottomland. A vernal pool is this picture right here, right? We can walk in Ruger Woods and there's a tree that fell over, ripped up, a big part of its root system and left a depression in the ground. Snow collects when it melts in the springtime. It's beautiful habitat for our amphibians, right? Very important. It's called vernal because that means spring, but it's also ephemeral. They call it ephemeral or fleeting. It's not always there, an ephemeral pond. They dry up in the summertime, okay? So that's a vernal pool. A peatland, no need to kind of remember this one. I say it rarely, but it's made out of peat moss, okay? So it's kind of like a bog. And I would rather you memorize bog and keep track of that. So a bog, it's dominant vegetation. It's not going to be trees like a swamp. It's not going to be herbaceous material like the cattails in a marsh. It's going to be the sphagnum moss, as I mentioned, right? So it's like peat moss, right? It's spongy, like the boreal forest has a lot of bogs, okay? And the water that is in this wetland is coming from rain, okay? In addition, it's very acidic, right? The soil, if you were to kind of do pH on it, it's going to be acidic. Now, up here in a fen, that's another type of wetland that gets its water from other moving streams that are kind of coming through it, not from the rainwater like we saw with the bog. And if we did the pH on that, it's going to be fairly high. So alkaline, okay? This is just a visual of what it might look like if we were to kind of cut through the soil in a bog, right? You're going to have the water, and then you're going to have the spongy peat, and then the peat's going to dry out a little. You'll have woody peat, and now you'll be kind of back on main land, okay? Trends with the wetlands. Remember, things to remember with the wetlands, right? Always water. Vegetation adapted to water and soil is different from the surrounding soils, right? Memorize a couple of those types, right? Some of the things that we talked about. We are losing wetlands like crazy. And that is really the big threat to the wetlands. They're being filled for development, okay? Now, for example, where Chip Cummings Field, the baseball, field is up at our school, that was more wetlandy, and they actually brought in fill from like the Walmart construction to put in there to kind of raise it high and dry it out. There's some drainage tubes that'll run through. If you're ever walking in the woods, you might see some drainage tubes. But anyways, you'll notice percent wetland lost here, 50 to 55%, right? And you can see there's, parts of our country that are losing an awful lot of the wetlands. Okay, so now we're moving into the marine system. Okay, this is the saltwater system. And these organisms have to adapt to the stress of being in salty water. And so salinity is a concern, right? They have adaptations to deal with a halocline. Halo is salt, cline is that change, right? We talked about thermocline, the change in temperature. Halocline is the change in salt. So these organisms are going to have adaptations to deal with salt. You've probably heard of like they're isoosmotic or they're hypoosmotic, right? They're changing their chemistry, the chemistry in their blood and whatnot inside their body to either match that of the stuff that they're swimming in, right? So in order to, if they're like, if their body chemistry is salty, then they will take in water into their cells to balance, okay? And vice versa. If they're not, then they'll release some salt so they can be in balance with the salt outside, right? And so that speaks to their waste. What are they excreting? We'll talk about that in a sec, okay? But they're trying to balance with their salts inside with the water body that they're swimming in. They also have to deal with acid, the acid in the water, the pH of the water, the pressure. If they're, down at the bottom in the benthos, they're dealing with pressure differences, the temperature, right? Their body's going to need to accommodate, the seasonal changes in temperature. If it gets cold, and we're talking a shallow water body, marine system. Light levels, right, only restricted to the top, right, where the algae can grow, where the plants will grow and photosynthesize. Predation, they can move, deal movement. We learned about that as a way to escape predators. And then buoyancy, if they're going to go really, they might need a way to kind of float. And so you'll see they use oils sometimes. Now, the salt thing is the big thing in the marine system, right? And this is a cool example, right? These organisms are consuming food in the water, right? And there's an example, most of the bony fish, most, mammals, amphibians, and so on, birds, reptiles, most of our fish are going to excrete urine as ammonia, okay? So it's going to be like dilute, lots of water leaving their body, excreting out this kind of salty water as ammonia. And then most mammals and other amphibians and stuff are going to kind of concentrate that a little bit more, retain some of the water, and they'll excrete more of a concentrated form in the form of urea. And then most of the reptiles are going to have even more concentrated. They're really hanging onto the water, right? A lot of the reptiles are in the desert, so they need to retain water, right? And so they excrete just kind of a clumpy, uric acid that kind of is found on rocks and stuff out in the ocean. What is interesting though is in the ocean, think of a dolphin and think of a shark and a ray, okay? They actually have evolved different things to do. So the dolphin acts more like a regular bony fish. It's going to excrete as like ammonia, right? A lot of dilute urine. But the shark and the ray are actually going to retain some of that ammonia, and they're going to retain some of the urea in their bloodstream, which will allow them to better deal with the salt issues that they've got. So it's kind of an interesting adaptation that these guys have. Temperature adaptations. Some organisms are going to actually have proteins in their body that will help them not freeze. So imagine the Arctic fish, they have these cryoproteins. Remember cryoplanation, right? Cryo, the freezing. And so they've got these antifreeze compounds so their cells don't freeze, and that helps them in the Arctic. And then our rainbow trout in our streams up here actually will produce an enzyme during certain seasons, which will help them better adapt to the temperatures that they'll be experiencing in the stream system, which is kind of interesting. Now, one unique place in the marine system is the rocky intertidal. Anybody ever been out to California? Yeah. Their California coast looks very different from the New England coast, right? The New England coast maybe has, you can walk for a long distance in the sand out to the water before it starts getting deep. The rocky intertidal has these sharp rocky ledges, right off the edge of the coast, right? And so think of the adaptations the organisms need to have to live in this kind of rocky habitat. These are the kinds of animals you're going to see: crabs, starfish, mussels, limpets, the tiny little kind of shells that you see on these rocks, like you can see pictured here. And some of the time they're going to be dried out, right, when it's low tide versus high tide. So they have to deal with drying out. They have to deal with the stress of being whacked with the waves. Predators like crabs are going to be around kind of eating them, and they need to compete for the space on the rocks. So these are the stresses that these kinds of organisms that live in the rocky intertidal part of the marine system, so right on the coast, the rocky coast of the marine system on kind of the west coast. Also another kind of habitat, the estuary, right? That's the meeting of the fresh and saltwater systems. Very highly productive kind of habitat. Just be kind of aware of that term as well. So here's just the zonation of the rocky intertidal. You'll see the waters right here. Then you start having these seaweeds, different types of seaweeds. Now you've got kind of the clustering shellfish, the keyhole limpets and barnacles, little periwinkle snails, and so on up to kind of the typical, mainland scenario here. You'll notice life is tough. They're going to have really strong holdfasts. Okay, so these are some of the adaptations to living in the rocky intertidal. They're going to have, these byssal threads, these hairs that actually they're trying to like synthesize these companies are trying to take advantage of knowing how strong these are, that these shellfish can stick onto these rocks up against massive storms and maybe make fabric out of this, right? Like maybe this is our new smart wool, right? So that we don't have microplastics in the wash. They can also do vertical migration to avoid the desiccation of, low and high tide. They have shells that are calcified, which helps them in drying out and being eaten by, other things too. And they can hide, right? Hiding in their shells. Now, in the marine system, there's also zonation. Remember, we had talked about the limnetic zone and the littoral zone in our ponds. Now we've got the epipelagic, epi the top, right? Epi, then meso, right? Pelagic being kind of the ocean water. Bathy, you've probably heard of bathymetric, right? Maybe. But that's deeper. And then the abyss and the hadal zones, right? Way down, kind of like compared to the benthic that we saw in our lake systems. How do these guys deal with it? Well, they don't have a place to hide out in the open ocean. They've got to deal with gravity and sinking. And so some of their adaptations are counter shading. So look at the bottom of these fish, right? Imagine the moonlight shining down. It can actually you won't be able to see that there was actually a shadow there if they have some of these abilities to kind of counter shade with their coloration. And then others will, change the surface area to volume ratio. They'll have small body size so they can kind of float. In terms of, needing to stay up at the top, they can have swim bladders, a unique kind of organ that will allow them to retain the buoyancy. It can fill and deflate during different times. In addition, they can have some oils that they retain, which will change their buoyancy as well, and they can stay higher up. cold, right? The organisms deep in the ocean, down in the Hadal and the abyss areas, they're dealing with cold, really high pressure. It's dark down there. And where are they getting their food, right? Because it's up in the epipelagic area. What if they, it's dark and they may not ever find a mate, so it's problematic, right? But oxygen's not a problem because there's a lot of oxygen in these colder waters. The adaptations to the organisms that live way down deep, they can light up, and that helps to distract against predators and to kind of call attention to themselves when they want to mate. They also have crazy, mouth adaptations and light organs and whatnot, that will help them in consuming some unique things. There's vents, hydrothermal vents. You've probably heard of them as well, kind of where the tectonic plates meet, down in these deep areas, is a unique kind of microhabitat. And the organisms that live down there kind of look like, if you guys watched Avatar, I haven't watched it in a long time, but there's like these wormy tube, like wormy things that like have plumes when you walk by, they would like open up. And so instead of using sunlight to gain energy, photosynthesize and have energy, and be able to eat them because they live way down in the deep, they actually are garnering energy from sulfur that's being emitted from these cracks in the ocean floor. So hydrogen sulfide down there. And so these are all little tube worms. I actually had a colleague in grad school who was studying tube worms. She went down in one of those submersibles and brought like a styrofoam cup. And when you go down that deep, it like totally shrinks up. So she was bringing these things back to us. So really interesting, the organisms, giant clams and these neat kind of tube worms that use sulfur as their energy source. A similar type of habitat, the cold seep. Another area that's very cold. The energy in this case, there's a lot of bacteria that are down there in this cold water. They're methanogenesis. And so they're using methane and converting it to carbon dioxide. And that's the chemical energy they're gaining from the bacteria down there. Similarly interesting organisms. You can kind of see them down here. They look kind of urchiny. There's some crabs. These organisms that live along the coast, this is a marsh, right? You can see that's a marsh here. They have saltwater marshes. It doesn't just have to be a freshwater marsh like we talked about. There's going to be zonation, just like along the Rocky Intertidal, right? Nothing you need to kind of memorize, just know there's patterning, okay? You might hear someday, the term infauna versus epifauna. Infauna, imagine you're walking in the sand and something squirts, right? Well, that is a clam, right? That's in the sand. So that's infauna. Epifauna would be the organism living at the top of the sand, okay? And these are just, if anybody likes going to Cape Cod, these are just some of the plants and animals that you might encounter in a sort of marine, so saltwater marsh system, okay? Spartina, Juncus, bayberry, sea holly, these are kind of the grasses and the shrubs that you'd find moving up the coast to the big dunes, right? And then mussels, these are the clams, right? The black clams that you saw with those threads. Periwinkles are the little snails. Brine shrimp, you guys have seen sea monkeys, that's them. And these tiny little fish that can deal with the salt, right? Mangroves, these are another marine system. This is kind of the islands you find off of Key West and some of our Caribbean islands. They're really interesting plants. They basically grow with these aerial roots that allows them to deal with salt and low oxygen or anoxic water. So most of the coastline in our tropics is lined by these, and it's good because the water of a storm surge, a tsunami, a big storm, a hurricane, is going to crash against this kind of habitat before it's going to crash against the mainland, right, or the island system. So these, are, aerial shrubs, right? They collect mud down at the bottom. They can tolerate the salt very well. They have these pores on them, on those roots, called nematophores, and that releases the salt and helps in gas exchange. So the nematophore is kind of like the stomata. I mentioned sunken stomates with the desert, right? They're gas exchanging pore. And this is kind of what it's called here in the mangroves. Coral reefs, we're getting to the very end here. Coral reefs are, you know, obviously very productive, high biodiversity, living organisms. Corals are animals. They're found in the shallows when they, you know, they have hard skeletons. But they have a partnership, and the partnership requires us to have healthy waters and not too hot, right? And so they have a partner, this photosynthetic zooxanthellae, and that partner is going to be giving energy. So it's going to be photosynthesizing, giving energy to the coral animal, and the animal's then giving it a place to live. And it's kind of a back and forth give and take. When the waters of the ocean get too hot, they expel the zooxanthellae and will die. So if you're ever snorkeling and you see kind of all white coral, that's not the usual. That means that it's a dead skeleton of the coral. And again, the coral is going to feed on zooplankton as well. So those massive bleaching events that I mentioned are, you know, the coral reefs bleaching. So in terms of fun facts, just letting you know, there is an invasive starfish. It's called the crown of thorns starfish right here. You can see it. It is taken over and wrecking our reefs. Somebody dumped it, and it's gone crazy and growing, and it's killing the reefs. Caulerpa taxifolia, another invasive species. So those are two invasive species. Imagine aquarium plants that got dumped down the drain when you were cleaning out your aquarium, and it went out into the water, into the Mediterranean, okay? And it spreads really easily, and every time it breaks, it like fixes itself with glue. So it just keeps creeping and breaking, and that's fine, and nothing likes to eat it. So it's a huge, huge problem. They don't know how to get rid of it. The only way that's been successful is putting tarps down and bleaching it, but then it kills everything else. That's really not the best way to treat it, right? And then great white shark nursery. This is a good thing. Anybody who's ever been out to Long Island near Montauk, there's a nursery where they found a bunch of these, you know, sharks that are giving birth out there. So it's a pretty cool scenario. Awesome. We made it through biomes. All right. So if you guys want to, with it fresh in your head, I would hop right down to the bottom, you know, jump on that quiz that'll open at noontime. And again, you'll have a half hour on it. No homework. If you haven't done the biome homework yet, please do. If you have, well done. They've been great. And I hope it reinforced kind of what we've been talking about. So we'll pick up on Monday with limits to organismal distribution. Okay. Have a great weekend. Happy Valentine's, everybody.
Thank you. Have a nice
Bye.
day.
Happy Valentine's.
Thank you.
Yeah.
Thank you.
I hope I get my, what are they, Cadbury mini eggs. I might have to buy them for myself. Bye.
Bye.